Right, and we're going to kick off with our first talk in this session, and we're going to hear about someone who has experience of teaching Rust and explaining Rust to people and learning what it's like. Some of us on the embedded working group, right, we forget this stuff because we've been doing it for years and our heads are right down in it. So I'm really looking forward to this talk. Please put your hands together for Oliver Scherer.
Thanks. Hi. So I'm Ollie, Ollie OBK. You might have seen my question mark somewhere before. I'm a researcher at KIT, which is in Karlsruhe. And 5 years ago, I started working there. And once Rust became 1.0, I started offering a yearly practicum for teaching Rust and embedded to students. So as per academia, I'll have a nice list of what I'm going to talk about today. So in the beginning, I'm just going to show you what happened over these last 3 years. And then I'm going to go into the problems that my students had and the various things that actually ended up working and how I changed how I teach Rust over time. So in the first year, I had a research assistant, and you might have heard of him, Philip Upperman. He has written the OS designing blogs. He basically wrote all the drivers and all the support hardware, support software. And we decided to go a different route that was popular back then. We tried to make everything by ownership semantics. So in the beginning, most Rust embedded development was similar to C embedded development. You had lots of static variables. Everything was kind of global. You just were accessing your hardware and everything. Well, it worked. And we tried to use the ownership model. So you had a piece of hardware and you owned it. And if you gave it to a function, well, then it was gone. And if the function was using it, then you're lucky, and it probably does something good with it. But other than that, you were moving around your hardware in your software too. In the first year, though, we didn't have many high-level abstractions. We were basically we had some basic things implemented. We had some display. We had some LEDs. We had audio input actually. But we didn't have more complex things that the hardware offered. We were using an ARM discovery board, which had like all these neat kind of things on it, and students could only use like half of them. This will change over time, obviously. But also in the first year, we had none of the cool features that we take for granted with Rust today. We had no RLS, we had no Clippy. We didn't have embedded targets on Rust Up. We had to use Xigo to build them. Thanks, Joche. That's really helped us. And there was no Hell ecosystem. So yeah, the first day was basically setting up Rust. And in the end of the day, we actually managed to get something running on the controller maybe, but it was like building Clippy, building RLS, getting everything of that set up. That was in 2017. In that year, around a fifth of the students actually had programmed in Rust anything before. Like, I'm not even saying like they wrote big projects, it's just they ran cargo run on some project. Around a third knew embedded, had developed with it before, maybe through the Java embedded things or on some other more dynamic languages, but a few of them also had programmed in C or C++ on embedded before. But that was around the rate that we had in the first year. After that year, some students actually implemented more stuff for us. They used the practicum to write new drivers and such, which we integrated into our whole system, so the next year students could make use of that. So we actually moved over the course of the practicum to have more support for things, and we also ended up fixing float support because students were attempting to use lots of floating points on embedded, which surprised me, but they were writing games, so I guess, yeah. I also had a student doing a bachelor thesis, and if you've ever used Crossbeam, it's super fun to use threading with that. And I was like, maybe we can do that for interrupts, and well, he did. So we had a Crossbeam-like API where you could just create interrupts that are closures, actually, and they can share data with everything, and you have some mutexes to share the data between the interrupts and the normal code. And then, the API looks like what you know, so you just keep on writing the code as you did, and you don't have to do some static variables to exchange data between interrupts and your main code. And so yeah, that was pretty cool. We had that in the next year. So in the next year, we actually had RLS and Rust up. So that was already, took us off like an hour of the whole setup process. We still didn't have Clippy, but, well, Clippy was an RLS, so we didn't have to have Clippy. We could just told, well, you can't run cargo Clippy, but you can just use RLS and it'll Clippy lint your stuff. We still didn't have any ARM targets, so we were still using Sargo, but we had set it up in a way that students didn't have to notice so much anymore, but yeah, still had to happen. And also still no Hell ecosystem. But already a few more students knew about or had used Rust before, so this rate is going to keep increasing. But embedded just stayed at a third. I was asked this question of the group and a few others, but the other questions never changed between the students, so I don't think they're interesting. But what we also got, we now have async await abstraction. So instead of doing all like one big main loop and implementing the whole structure in a way where you poll and then you work with it and you have to kind of manage your own scheduling by saying, okay, I only execute this poll every 5th iteration or something. No, now we have async await, and you can actually have like little closures that that are interrupted by you telling the closure to now you may get interrupted. So it's cooperative multitasking. We had that. I'll come later back to this, why it's not a good idea to expose this to students, but it was fun. So this year, we had all kinds of neat things. So the practicum was like a month and a half ago. We had everything. We had RLS and Rust up, Clippy and Rust up. We had the ARM targets that the people would just like Rust up, component add, or no, target add, and then you had that. And we had a bunch of HAL ecosystem crates that we were using. We still need to upstream more of our stuff. It's like still partially bundled into our code, but yeah. So suddenly, 2/3 of my students already knew embedded. I don't know what changed, but maybe IoT. I don't know. But we have a lot more embedded students now, and well, the Rust rate also went up a little bit. But, well, all this worked really well, and students had a lot of fun, but there were lots of problems that we had. So I'm going to go into what kind of things went wrong. So first I'm going to go into what Rust things went wrong, but then I'm going to go over to the embedded part. So Rust things, well, lifetimes. If you ever had a beginner Rust developer and they got an error from the compiler, something does not live long enough, what's the first thing they do? They add another lifetime. And then they get another error, and they add another lifetime. And, well, OK, this is at least how I did it and how lots of students did it. So, yeah, at some point you realize, OK, if the compiler tells you to use a lifetime, maybe think about what you're doing and not use lifetimes, and it often works. So 90% of the times where students were complaining that they had to add too many lifetimes, we figured out a way that they didn't need to add any lifetimes, and everything worked exactly as they wanted. They were just like thinking about it not in a Rust way yet. That's the problem. You need to learn Rust. You need to think about how everything works in a Rust way. Also, that's not really Rust general, that's more programming general, but like, yeah, if you start using hacks early in your project development, well, and then you add more hacks because the hacks don't quite work so nice, then at some point you get stuck. This year I had a student come to me on like the second day, and they had a problem, and I told them, okay, so the right way would you be address this, for example, with enums or with traits, and they had like this big setup where they're basically emulating inheritance via some references and whatnot. And yeah, so they had a very simple problem actually, but they were over-engineering it a little bit. And they were like, yeah, but it works for me right now, and I'm just going to add a few more things. I don't need it to work all this way. So go to the second week of the practicum, they're like, okay, everything I wanted to do doesn't work anymore if I keep doing this, so I need to refactor now. So yeah, not really Rust related, but always, don't do too many hacks. One thing that happened every year, there was always a group which never got the thing to compile in the first few days. They were working on something, they were designing something, and after a week, they got the first compile. They were really frustrated that it was always one group in the whole thing. I don't know, we had like 7 or 8 groups, and but every year I had one group, and once they got it to compile, they were so happy that it finally compiled, but they were like, okay, we have 2 more days. How are we ever gonna get this to work? And then like, oh wait, it works. So welcome to Rust. It's just so awesome. Once, like, if you're designing something complicated and it has lots of generics and lifetimes and everything, but you know you're designing it right, and you keep working on it, and at some point it compiles, like almost all the time, you end up having it actually do exactly what you wanted at runtime too. And this was developing on embedded, so they couldn't always run it on the computer, but most of the groups there that were doing complicated stuff like this, they were doing the method where they were implementing like a backend that works on a normal PC, a backend that works on embedded, and then we're just switching between it. But yeah, getting it to compile, that was really a success for them, and they were so happy about that. So, well, it's not just Rust stuff that we had problems with. Usual embedded stuff, sometimes a little bit Rust related. For example, well, there's no heap on embedded, obviously, but like we can do a heap, but like we offered them the alloc crate and they were using it, and then when they made their own project, they were suddenly wondering, why doesn't it work anymore? Like I was using the official example project and everything worked. We could use vectors, we could use strings, and then they're like, now I can't even allocate a single byte in a string or something. And well, they forgot to initialize the heap, which is something that is currently a Rust problem because we can't create other heaps than like the default heap. And if you create the default heap, it needs to be created before you ever try to allocate something. So yeah, heaps are a little bit fun, but usually it was just like they came to me, hey, I can't allocate anything. It's just always out of memories. And I'm like, okay, let's look at your code. Okay, maybe you try to allocate before creating a heap or something. So yep, that was like half the groups had basically this problem. Floating points. Well, at the beginning, floating points didn't even work with just plus and minus and so on because we were still figuring out the hardware. But the moment something works, people want more. So they want like square roots and sinus and whatever they're doing. They're writing games. I mean, for games, you need all kinds of these methods. So we have libm, and this is the most awesome thing. The students came to me, they were like, okay, we already implemented like this table for sinus and so on, but we also need the inverse, and they were trying really complicated things, and I was like, let me hold you there for a second. Crates.io. So we have this crate, you add it to your cargo toml, and then you use the crate and get, for example, the sign function out of that, and then, well, it works. And they were like, wait, I don't need to do anything. I don't need to link it. How does this work? This is like for embedded. So this was feedback I got from the students every single time. They loved Crates.io, just like totally. It was like, this is one of the sellers for Rust and embedded. Like anything else, so the security, the nice features from the language and so on, they're pretty cool. They make everything neat and close, but like, just having a Crates.io ecosystem where you can just get a crate and it works, that's just such a productivity bonus. I don't know how they would work without that. They were using so many crates in this project, and this was embedded. I mean, we don't even have that many no-SCD crates, but there's enough of them for it to be like to work really well. But then they were using lots of math. And then they were using really lots of math because they were writing games where there has 100 objects flying around on the screen. And they want to calculate new angles of those or something. So they started using lookup tables and so on by using the libm crate to generate the values at the beginning and then just looking the values up in the future. And this worked like a charm. Like if I suggested that, they came to me after half an hour. Okay, it works, thanks. it's just like they just wrote it down. I don't even often don't know how they implemented it, but sometimes they were just using vectors or something, or like even using memorization to just, well, the values that they need often to just cover those. Then the hardware we're using had a random number generator. Same problem again. It was super slow because that hardware is not meant to generate like 1,000 numbers every frame or something. So they were using the rand crate from crates.io again. They just added a no-stud feature. They were ready to go. They generated a new number generator, gave it an initialized seed from the hardware because the hardware has real randomness, and off they went. And they had random numbers as much as they wanted, as fast as they wanted them. So, yeah, again, crates.io. It's just so cool. Okay, and everybody who was writing drivers, yeah. This came up every single time somebody wanted to use new hardware that wasn't used yet. They were using the registers. I tried, I don't know, somewhere there, I was not bringing over the point. I brought this up multiple times the first day. Like, if you ever use any of this hardware stuff that's not already nicely abstracted away, if you're trying to do anything new, there's some clocks that you need to turn on. And if you ever want to start with that, talk to me first. And yeah, no. They were writing to registers. They were reading the same register again, and then it didn't change. I was like, okay, let's turn on some clocks. Another fun thing, well, this is a microcontroller. And, well, people, when they write games, they want pictures for those games because games are prettier if you have pictures. And then they were using a very simple method by include byting, for example, just a GIMP outputted binary version of a picture, and they were using that picture. And it worked. And they were happy, and then they were using another picture, and another picture, and another picture. And at some point, it was like they were getting linker errors, and they were horrified because they'd never seen a linker error before. And yeah, so we had like 1 or 2 megabytes of RAM, I think, and we had loads of flash. But at some point, even 8 megabytes of flash are gone. And yeah, well, it's an embedded device. It's a microcontroller. Not even that. Like this is pretty big for a microcontroller. But yeah, usually we figured out some way around that. They started moving to indexed instead of RGB. So we're having color maps or compressing the pictures in some other way, and that usually worked really well. Yep. So yeah. I was teaching this for 3 years, and every single time I wondered what could I do better. There's one cool thing my university offers, which is like an anonymous review or evaluation of the process, where afterwards I get written answers, or I get like automatic, just like between 1 and 5, choose something. And I got back to those later, but like generally what I was looking at was taking notes whenever students came up with repetitive problems or something, and tried to figure out how to improve the process. So one thing that obviously is clear, and not just in hindsight, as teaching is not just throwing information at your students. If you want to do that, take a big book, and it's about as effective. Like I moved to basically having very short teaching areas where maybe I teach them a new concept in Rust for like maybe 20 minutes or something, and then there's a time frame about the same size where they can use that. I give them a problem, solve this, like write a Fibonacci, and then write a Fibonacci that's actually performant or something, and so on. Like these are very academic problems, but well, they're learning, so it doesn't need to be a realistic problem. And so, oops, I thought there was not a slide there, sorry. So yeah, students were much happier this year, I had the feeling, about the way that the teaching process worked. So we have 2 weeks, and in 2 weeks they're supposed to finish a whole project on the embedded controller. And the first year I had 2.5 days where it was just spending those days teaching them how Rust works, how embedded Rust works, how embedded problems work, how to read a data sheet. And it's just like such a big block in the beginning. Nobody can memorize all this. So yeah, we changed that later. Also, lifetimes, I tried to teach them. It's not that I gave up. But yeah, the students are, I give them problems to solve, and then I explain them what problems, how to solve this problem by letting them first work on it and see how far they get with the compiler. And this year, this has been much more effective. Like the first time, I just had students come to me and like not ask anything except, I don't understand lifetimes. Like and this was like second or third day or something. And this year, I had basically none of that. So yeah, I thought we had 2.5 days in the beginning. Right now, we're down to half of that. So I have the first day where I teach Rust, and then we immediately go to the embedded device, and they can just play around with it a little bit. And the second day, we start from scratch. I teach them how to build a whole project for an embedded controller from scratch. And yeah, so this year the students were much happier. The first years I always got complaints. There was too much theory at the beginning and so on. This year they were pretty happy with how it worked. So yeah. There's also some conflict between different ways students like to learn. Some of them, they want everything up front. They're like, oh damn, now we're in the second week, we need to finish the project by tomorrow, and if I had known that XY thingy at the beginning, then I would have written my whole code in a different way. Well, yeah, but then you would have never gotten to writing anything, because if it would have taught you everything that you could ever need to know, then we would have gotten there. And it feels like a dilemma, like where do you find a balance? And I've basically gone to the point that you don't need to finish a perfect project in just 2 weeks. That's not the point of this practicum. The point of the practicum is for you to learn about Rust, about embedded, and how to write software in that niche. And some students were a little bit frustrated about not being able to do things better, but mostly they, I think, got that point, and they were pretty happy at the end. It's like we always had a finished project. They had something to show. So at the end of the project, they always made a presentation where they showed what they finished in those 2 weeks. And I'm going to show you a few of those examples. So this is our controller. It has a touch screen. It's about as big as a small smartphone. It has all kinds of things. It has 2 microphones. It has like all kinds of plugs where you can connect Ethernet, where you can connect headphones, microphones, and whatnot. And in the second year, a few students, they were using those 2 microphones to pinpoint where people were talking in the room. They were like, you put this in the middle of the room, and then it was showing you angles where the loudest person in the room was. So yeah, we had that. This year, somebody wrote a driver to actually use the headphone output. They made a small board where they could record sounds and then remix them, or play like a keyboard on the touchscreen and so on. So yeah, this offers a lot of convenient hardware things that students can use. One example is always games. We always have like half the people writing games because games are fun. And so this is from the first year. People wrote a whole render pipeline for a kind of, oh, there's no English word. It's called Mohun. So you basically just click on the screen and shoot something that flies by. And they wrote a whole render pipeline for this game. And this was all written in Rust on the host machine first. And they were using a small game engine to just render it to the host computer, while another team was writing the back-end game engine, replacing the host game engine just for the embedded device. So there were teams of like 2 or 3 people, and they split each other up so everybody could write one specific part. And in the end, they had a working project. And since they were working with Rust, where they could define their APIs nicely, this actually worked out super well. They were just like plugging things together, and sometimes had a few conflicts, but other than that, it just kept on working. Somebody who has never written Rust before, never written embedded before, they wrote a UI toolkit for Rust on embedded. Those were the people who took 6 out of 9 days to ever get something that actually compiles. And in the end, they had something that was not just a UI toolkit, it was a multi-touch UI toolkit. You see these 3 boxes? Those are windows that you can drag around all at the same time. For the showcase, they were dragging around these 3 boxes, they were clicking buttons, and the buttons were generating new items, and this was all unembedded. It rendered in full, I don't know, 30 to 60 frames per second. There was no flickering. It was amazing. So, yeah. Oh, you can't see that here very well. Another group was doing networking. So they were writing basically a network analyzer. They plugged it into any random network, and it was printing out colors in rows, depending on what packets were coming in. So it's just like a nice visual representation. But this year, somebody took it one step further. They wrote a, network bricking tool. So you get like the screen, and you connect it to the network, and then there's like one button in the middle of the screen, and it's like connect Ethernet, and you click it, and there's like text coming on top. So like connecting Ethernet, okay, you have a MAC address, everything works. So you're like, okay, now you have 5 buttons. It's like fixed IP address. They gave you a few examples, but also like DHCP or automatically finding an IPv6 address. So you choose whatever you want, you click on the button, and then a whole new menu pops up. And that menu was just like amazing. There was a log on the left where you could scroll, and on the right there were buttons. And the buttons were at first very simple. There was one like scan the network for IP addresses. You click it, and new IP addresses show up on the left, and you're like, okay, cool, that's cool. And then you select one of the IP addresses, and you're like port scan, and then it starts scanning commonly no ports, and you get a list of what ports are open on that device. That's the benign part. At the bottom, there were 2 buttons. Those buttons had the same color as all the other buttons until you pressed them. When you press the one button, it actually just takes over the network by making an ARP spoofing of the entire network. So you have this tiny device that you just plug into a network, you press a button, and suddenly all traffic routes through you. And you can do whatever you want with that, obviously. The other button was, brick the network. So nothing worked anymore. It just kept spamming the network with things that usually break networks, like, doing weird kind of ARP spoofing, or like even changing its own MAC address to be the MAC address of other devices. No. Okay, back to less aggressive topics. People were also writing raycasting on the microcontroller. So raycasting is very slow, obviously, on such a controller because it's very resource consuming, but it doesn't need that much RAM. So they wrote all kinds of complicated things where they had mirror spheres and all kinds of surfaces, and they had textures for those. Sometimes the textures were auto-generated, sometimes they were included as pictures. And then they started rendering those, and you could see like it was building up pixel by pixel on the screen. And they made it even permanent. So if you turned off the device and just turned it on again, it just kept rendering where it was before. So yeah, that was pretty cool. Some people were writing drivers. This is the log of an SD card driver. Because the device, the controller has an SD port, so you can store up to, I don't know, 16 or 32 gigabytes, or how much the hardware supports. And they wrote not just a driver, they also wrote a FAT, the file system, and so they could access the files in a normal way. And yeah, so these kinds of things, we started including them back, like porting them back to our main library, so next year students could keep using those. But students always wanted a little bit more than we had to offer. So this one is very personal for me, const.fn. We have gotten const.fn stable last year, so students were actually able to use them this year in a stable manner. But there's so much more that we could have and that they were asking for. It's like they were immediately trying to load the pictures as bitmaps, like not bitmaps, like BMP pictures or JPEG pictures, decode them with something, and just store the final coding that they wanted. I was like, yeah, I want that too, but sorry. Then resource exhaustion. So if you're using too much RAM, so you get out of memory, or if you're just using statically too much resources, you get a link error. And lots of these errors are very hard to comprehend, or at least hard to understand where you can optimize to make it better. This is something that we should work on. And amusingly, nobody at KIT seems to be using Rust other than me. I've been trying to push more for this, but so far it's, well, academia. Everybody's using their favorite language, so there's as many languages as researchers. So I guess we'll need to wait a little bit more on that. We had some things that students really liked that they specifically said that they liked. So again, Crates.io, even together with Snowstood. For beginners, Clippy is also a super cool tool. Even on embedded, it'll tell you loads of stuff that is very helpful. And in general, just compiler errors, they were so much more helpful than what we get from regular C compilers. That yeah, students mostly came to me and were like, "What's this problem that that the compiler has with me?" And I was like, "Well, scroll down a little bit further," and they were like, oh, right, okay. So mostly it was like learning to read compiler messages again, because, well, we have all been trained to not read compiler messages from other compilers. So back to the evaluation. This was anonymous, so I don't actually know much about this, but I know they like the relaxed atmosphere. So just, yeah. In German, we have a separation between like personal you and more formal you, and even that, people were just coming to me. We were just talking normal first name basis and whatnot, and they really said that they liked that. So I hope that it made them ask more questions or be more willing to ask for help. And yeah, they also wrote that they liked having a dog in the event, which was pretty cool. Like one time I had a student come to the front, and he was like, just came here, looked like he was trying to ask me something, and just started petting the dog, which a lot of them did. But then he was like, yeah, I don't have a question. I just came here to pet the dog. So, yeah, teaching has some different challenges than what we have in general open source, because in open source, people come to do something they like. In teaching, you also have lots of students that just are here for the credits. They might come here because it's something they like more than the other stuff. That doesn't mean it's like the thing they really want to do. It might just be for the credits. So there's some difference in how you need to push information to the students. Also, well, Rust isn't a silver bullet. Like we have loads of cool stuff that make everything easier, but you can't write good software just by changing a programming language. That's not how it works. But nowadays, like even Hell and so on uses loads of ownership semantics, and just combining all of this makes it so convenient. I sometimes had students come to me about problems where the compiler told them, no, you can't access this, and they were like, why? Like, I just want to write to the screen. And I was like, yeah, but you also registered a log renderer that writes text to this very same screen. And well, you need to decide which one you want to do. You can do both if you want, but then you need to figure out how to share this information. And this was a very visual way to see where the problem is, because if your text is writing over, I don't know, your game characters or something, they immediately saw what the problem was if they were just using, like, I don't know, mutex locking the screen or something, and it just doing the same thing they were doing before. But now it was still safe, but like they saw the problems that are occurring with concurrently writing to the same resource. And yeah, so I told you about async await earlier. Not a good idea for students. It's super cool, but like if you try to understand what a compiler, what a controller is doing, going through it by step it's just easier to comprehend in the beginning. It's like you go there, you ask the hardware for some information, you output something to the screen, and at some point you're like, okay, I'm done, let's do this all over again. And then you keep doing that. And that is very easy to follow, also to step through with the debugger. If you move to something like async await, which stuff jumps randomly between different execution lines and decides on what is supposed to get executed. And your initialization is basically just like call this function, this function, this function, this function, this function in arbitrary order and, well, go. That looks super convenient. And for larger projects, that's I think, a way where we can do more in the future in cooperative multitasking. But for students, I'll stick to polling for now because, yeah, it just makes so much more sense to them. So, yeah, thanks for listening. And if you have any questions about teaching or, well, embedded development in academia, I'll be happy to talk to you about that.
Now, I can already see some of you are desperate to ask some questions. In the interest of time, I'm going to suggest we save those questions for the break later. If you're going to be around, so yeah.
Can I have one more? Sure. So I brought a few of those controllers with me. So if you're here in the next 2 Impl days, also come to me, and then we can talk if you want to hack on those.
Cool. All right, once again, put your hands together.